Hello and welcome to this Introduction to Microbiology video. I'm Dr. Allard Roberts, and in this video we're going to look at antibiotics, what they are, how we might classify their activity, and just some more general effects they have on bacterial cells. Now, most people will have experienced a sudden fever, a sore throat, or an infection that seems to come out of nowhere. These are examples of acute infections where microorganisms enter the body and multiply quickly, prompting a rapid immune response. Now, in most cases, our immune system will act quickly and decisively to clear the infection and restore balance within a couple of days or weeks. But sometimes things don't resolve the way they should. If a pathogen manages to evade the immune system by hiding within tissues, forming biofilms, or adapting to its environment, the infection can linger. And this is what we call a chronic infection, one that persists for months or even years, causing ongoing inflammation and long-term health impacts. Now, when an infection becomes chronic, the immune system often needs help, and this is where antimicrobial therapy plays a vital role, which is where we use chemicals designed to kill or inhibit the growth of microorganisms causing infection, providing our immune system some much needed support. Now, when we talk about treating infectious diseases, we use different antimicrobial therapies depending on the organism involved. So for our bacterial infections, we use antibacterial agents, more commonly known as antibiotics. Antifungals are used to treat infections caused by fungi and yeast, which are structurally very different from bacteria and require completely different drug targets. Antivirals are designed to act against viruses, which aren't living cells, but infectious particles that replicate only inside host cells, and so they require very specific targeted therapies to limit the toxicity to the host. For parasitic infections, we use antiparasitic drugs, and for protozoan infections, we use antiprotozoals. Now, a key principle behind all antimicrobial therapy is that of selective toxicity, which was developed by Paul Ehrlich in the early 1900s, and this is the idea that a drug should harm the microorganism causing disease without damaging the host, acting as a sort of magic bullet. For example, antibiotics achieve this by targeting features that are unique to the bacteria, such as the cell wall structure, specific ribosomal subunits, or metabolic pathways that humans simply don't have. Essentially, selective toxicity is what allows drugs to work effectively, and understanding it helps explain both why some treatments are safe and why others have significant side effects when selectivity is harder to achieve. Now, alongside antimicrobial drugs, we also have some additional antimicrobial therapies in the form of antiseptics and disinfectants. Now, antiseptics are chemical agents used on living tissues such as skin or mucous membranes to reduce or eliminate microorganisms. They're essentially designed to be effective while still being safe for human cells, and some common examples include alcohol gels for hand washing and both iodine preparations and chlorhexidine for pre-operative preparation of skin tissue. Disinfectants, on the other hand, are used on inanimate surfaces like floors, equipment, and worktops. These are generally stronger and more broadly toxic because they're not intended to be used on living tissue, and so a common example is something like a bleach solution. Now, unlike antibiotics, antiseptics and disinfectants do not rely on selective toxicity. Instead, they act through non-specific mechanisms such as membrane disruption, protein denaturation, or oxidation, leading to broad damage in microbial cells. Now, at this point, we're going to have a more in-depth look at some terminology that surrounds antibiotics, which, if we remember, is a natural or synthetic chemical that kills or inhibits the growth of bacteria. And so our antibiotics can be classified based on how they are produced, meaning they can be natural or synthetic. Now, a natural antibiotic is produced directly by microorganisms and were typically discovered in nature without any form of chemical modification. So examples include penicillin, produced by penicillium molds as identified by Alexander Fleming's famous experiment. Synthetic antibiotics, on the other hand, are entirely synthesized through chemical processes rather than derived from a natural product. So an example would be ciprofloxacin, which is a second-generation fluoroquinolone derived by stepwise chemical modifications of nalidixic acid. Now there is actually a third group, and these are our semi-synthetic antibiotics, which are antibiotics that are chemically modified variants of our natural compounds. Now these modifications are typically done to improve stability of the molecule, increase its spectrum of activity, circumvent resistance mechanisms, or make it less susceptible to degradation. So an example might be amoxicillin, which is a variant derived from the modification of penicillin. Now, in addition to classifying antibiotics on how they are produced, we can classify them based on their general effects. And so we have three broad categories based on how the antibiotics kill or inhibit microorganisms. First, we have bacteriostatic agents, which don't kill bacteria outright. Instead, they inhibit their growth and reproduction, allowing the immune system to clear the infection, and some good examples are tetracyclines and various macrolide antibiotics which interfere with protein synthesis. Then we have our bactericidal agents, which actively kill bacteria, reducing viable cell numbers even in the absence of immune activity. And a good example is daptomycin, which depolarizes the cell membrane, resulting in cell death. And finally, we have bacteriolytic agents, which not only kill bacteria, but cause them to lyse or break apart, leading to a measurable decrease in both cell viability and cell numbers. And a good example are some beta-lactam antibiotics, which affect the cell wall, leading to a weakened cell envelope that ruptures. Now we can visualize these effects on a graph, and so if we were to plot the total number of cells on the y-axis and time on the x-axis, what we would see in any population that has ample resources is an increase in cell count over time as bacterial cells divide by binary fission. Now if we were to also graph the number of viable cells under standard growth conditions, we would see a parallel increase. But of course, this will change with the addition of an antibiotic. And so if we add an antibiotic with bacteriostatic activity, you'll see that both the total cell count and the viable cell count plateau. This tells us the population has essentially paused. The cells aren't dividing, but they're also not being lysed or killed. The antibiotic is simply preventing them from growing without actively killing them. Now, if we were to add an antibiotic with bacteriolytic activity, we'd see both the total cell count and the viable cell count drop together over time. Now, this parallel decline shows us that cells are not only dying, but are also physically breaking apart. So the overall number of detectable cells falls as the viable population collapses. And this pattern is characteristic of an antibiotic that is actively lysing cells. And now we come to our final type. What happens if we were to use a bactericidal antibiotic? Well, in this case, the viable cell count drops over time as cells are killed, but the total cell count stays relatively steady because although the cells are dead, they're not being lysed, meaning their structures remain detectable. This separation between a falling viable cell count and a stable total cell count is the hallmark feature of bactericidal activity. Now, in addition to classifying antibiotics by their general effects, we can also classify them by their spectrum of activity, essentially the range of bacteria they can inhibit or kill. And so antibiotics generally fall into two main groups. We have broad-spectrum antibiotics, which act against a wide variety of bacterial species because they target cellular structures or processes that are shared across many groups. In contrast, narrow-spectrum antibiotics are effective against a much smaller set of bacteria, usually because they target features that are unique to specific species or groups. Now, understanding whether an antibiotic is broad or narrow spectrum is crucial in clinical decision making, as it helps balance effective treatment with preserving the normal microbiota of the host and reducing selective pressures for resistance. And so, one of the key ways in which we use to differentiate bacterial cells and therefore predict which antibiotics might work is based on their reaction to the gram stain, which divides bacteria into gram-positive and gram-negative groups based on the structure of their cell envelope. This distinction has real clinical value, giving us an early indication of which antibiotics are likely to be effective. And so our gram-positive bacteria have a thick peptidoglycan cell wall and no outer membrane, which means certain antibiotics penetrate easily and work very well. And some examples of gram-positive specific antibiotics include linezolid, ticaplanin, vancomycin, daptomycin, and mupirocin. These drugs are generally ineffective against gram-negative bacteria because they cannot cross the outer membrane that they have. Gram-negative bacteria, on the other hand, have a thin peptidoglycan layer but an additional outer membrane containing lipopolysaccharides. This extra barrier restricts entry of many antibiotics, so they require agents that can either pass through porins or disrupt the membrane itself. And some examples of gram-negative targeting antibiotics include colistin, aztreonam, polymyxin B, gentamicin, tobramycin, and amikacin. But it's not always one or the other. Many antibiotics are broad spectrum, meaning they can act against both gram-positive and gram-negative bacteria because they target cellular processes shared across both groups, and these include our penicillins, rifamycins, tetracyclines, cephalosporins, quinolones, chloramphenicol, sulfonamides, and our macrolides. And so antibiotics can kill or inhibit the growth of very specific bacteria, or broad groups of them, in a variety of ways, and they have been truly transformative to modern medicine. Their introduction reshaped our ability to treat infections, made complex surgery safer, and dramatically reduced deaths from diseases that were once considered unavoidable. But with great power comes great responsibility. Understanding how antibiotics work and the principles that guide their use is essential if we want to preserve their effectiveness in the face of rising antibiotic resistance, because ultimately the choices we make in the clinic, in research, and as a society will determine whether these life-saving drugs remain effective for future generations. And with that, we come to the end of this video. I hope you have found the content useful, informative, and most importantly, easy to understand. Thanks for watching, and I hope you have a great day.